In this video, we'll learn all about Gauss's law, an extremely important law in the study of electrostatics in physics. Prior to understanding Gauss's law, it's important that you understand information about electric flux. We're going to take a pretty general situation to begin with. We're going to have a positive point charge, call it Q, located at the center of a sphere of radius r. That sphere of radius r is our spherical surface, or our closed surface. And we're going to start by looking for the flux through that closed surface. To do so, we're going to start by writing out our flux expression, which says that the electric flux is equal to the integral of E dot dA. Now remember, sometimes we don't need this integral, but let's go ahead and just start with it for now. That way we're doing it in the most general format. So, thinking about this sphere and the direction or the angle between the electric field vector and our little piece of area, you can see there's a little piece of area chosen on our sphere here, just to give us an idea of what's going on. We know we can always write dot product as the magnitude of one vector, the magnitude of another, times the cosine of the angle between them. And I know that the area vector of a closed surface is always perpendicular to the surface and pointed toward the outside. Now, I also happen to know something about the electric field of a point charge. I know the electric field of a positive point charge radiates outward in every direction. That means that the area vector and the electric field vector will always be parallel to each other, meaning that the angle between them is 0 degrees, and therefore the cosine expression is equal to 1. So I'm left with the integral of EdA. Now there's something else I know that's going to make my life convenient for this, and that's the fact that I know what the electric field is for a point charge. That can be expressed as kq over r squared. Now, if I think about this sphere is the center of the sphere is where the charge is located, and therefore every piece of the spherical surface is the same distance r away. That tells me that the electric field is a constant and can be pulled out of this integral. So now I'm just left with the surface integral of dA. And we know that when we have an integral of d something, that it just equals that something. So I'm left with E times A. But it's important to remember that this A is a surface area. We're talking about the surface area of our sphere here. So let's plug in our expression for E as well as the expression for the surface area of a sphere. So we have kq over r squared for E. And the surface area of a sphere is 4 pi r squared. So my electric flux is equal to this expression. Now, we can do a little bit more algebra to simplify this. Namely, we know K really stands for 1 over 4 pi epsilon naught. And then see how there's an r squared in the denominator here and in the numerator here? So those two things cancel out. So we're left with K, or 1 over 4 pi epsilon naught, times Q times 4 pi. And it's clear that that simplifies even more. The 4 pi's cancel out. And so we find that my electric flux here is equal to Q divided by epsilon naught. Now that's a pretty simple expression. It's really nice. And just a reminder, epsilon naught's a constant. You can find it on your equation sheet, but just so that you have it in your notes, it's equal to 8.85 times 10 to the negative 12th. And its units are basically opposite that of K, since it's in the denominator. So it's Coulomb squared per Newton meter squared. Now, let's go a little bit further into understanding Gauss's law here. So what if our Gaussian surface isn't spherical? Let's look at some examples of that. This diagram I have here shows 3 different Gaussian surfaces. And those 3 different Gaussian surfaces, which remember is just another name for a closed surface, is enclosing the same charge Q. This inner one is spherical, but then these other two, S1 and S2, are some strange shape. Now, because that innermost one is spherical, we know that the flux, electric flux through S1, that's my innermost sphere, is equal to Q over epsilon naught. Now, we'll say that this is the Q that's enclosed, and you'll understand a little bit more as we get further into Gauss's law as to why we specify that. So, we also happen to know that flux was defined as being, or it's really not defined as being, but proportional to the number of lines that pass through the surface. And it just so happens that the same number of lines pass through each surface because we have the same number of lines going outward from this Q. Now, we know often that, or kind of in general, that the electric flux depends on the electric field and the area. Well, it just so happens here that as your area increases, because we're getting further away from the object, my electric field decreases. So guess what? It works out that for all 3 of these surfaces, S1, S2, and S3, the electric flux can be expressed as the Q that's inside of that surface divided by epsilon naught. Because again, you can always draw a sphere inside of that irregularly shaped surface. This is the big idea of Gauss's law. In general, Gauss's law is the equation that the electric flux, or the surface integral of E dot dA, is equal to whatever charge is enclosed by that surface divided by epsilon naught. So this is Gauss's law, and it's going to help us as we go through looking for how to find an expression for the electric field of things that aren't point charges. One other thing to note is that if your surface does not enclose any charge whatsoever, then your flux is 0, and therefore kind of like either side of this expression is equal to 0.